Hello everyone. Today we're going to be covering Lab 2, the motion of a falling object. Our objective in this lab is to observe an object drop from rest that falls somewhat slowly, observe the effects of the forces of gravity and drag acting on the object as it falls to the ground, and create a model that accurately predicts the motion of the object based on these forces. Our purpose is to demonstrate how Newton's second law and the momentum principle can be used to predict the motion of an object under a non-zero net force, and demonstrate the relationship between a falling object's velocity and the force of drag. Here we are in Tracker to analyze the video of our falling object. In this experiment, we use a pizza box as the system, setting the reference length for Tracker equal to the height of the pizza box, 0.05 meters, and placing the axis at the center of the system's mass. As we look at the y position over time graph, notice the slope is negative because the object is falling down and is curved due to the acceleration that is caused by the force of gravity, but the slope also appears to flatten out here, the cause of which we'll discuss later in the video. Our first model predicts the motion of our pizza box in freefall. Recall that the final position equals the average velocity over the specified time interval. However, Newton's second law tells us that if there is a non-zero net force acting on the object, the velocity is not constant, so we will also need to code for velocity update. To do this, we need to determine the net force. Now, an object in free fall experiences only the force of gravity, which on Earth is equal to the gravitational constant 9.8 times the mass of the falling object, all multiplied by the directional vector, which in our code we call j hat. This product, the weight force, will equal the net force. After plugging in the mass of our pizza box, we define the weight force under the variable w, using the formula we just described. With the net force in our chosen time step of t equals 0.001 seconds, we now can use the momentum principle, dividing both sides of the equation by mass, to obtain our velocity update formula, which in turn will give us the necessary inputs for the position update formula described earlier. Our second model predicts the motion of our pizza box with both the force of gravity and drag acting on it. This means that although we can keep most of the code from the other model the same, there are a couple of key differences we need to account for. First, we need to define the drag force, which is proportional to the square of the velocity. The constant in this relationship is b, and for this lab, we find b through trial and error, running the program for different values of b until the final position in the time interval is equal for both the model and experimental data. The last thing we need to do for this model is set Fnet equal to the force of gravity plus force of drag. Since the drag force is working in the opposite direction of gravity in this case, we expect to see this acceleration in the negative y direction reduced compared to the other model. Now let's compare our data. As we can see in the first model, where gravity is the only force taken into account, there's a pretty big difference when you compare it with the experimental data. On the other hand, the second model, providing for both gravity and drag, we have something that much better resembles our experiment, although not perfectly, due potentially to distortion of the object's motion in the video by the camera angle or human error from recording positions in Tracker. Still, this second model is much more accurate. So what's the idea here? Well, since the force of gravity is working in the negative y direction, it is causing the box to accelerate in this direction, and position is growing more negative at an increasing rate. When gravity is the only force on the system, acceleration will continue infinitely. However, the force of drag prevents this, as it works against gravity in this situation, and since it is proportional to velocity squared, the faster the object becomes, the greater the drag gets, and the closer the rate of acceleration gets to zero, until it finally does reach zero, and the force of drag equals the force of gravity. We have a term for when this happens. It's called terminal velocity. Here's the velocity over time graph of the model with drag. You can see that the curve is becoming more gradual and appears to be approaching -2 meters per second, which is the terminal velocity of the pizza box. This means that because of the drag force, the box will not be able to fall faster than 2 meters per second. Once terminal velocity is reached, because velocity is constant, net force becomes zero, which makes perfect sense because the only two forces acting on the system, drag and gravity, have canceled each other out. Now let's look at the velocity over time graph of our gravity-only model. We can see that the slope of the velocity is constant. It continues to expand in the negative y direction as time progresses. This shows that in freefall, terminal velocity cannot be reached. Now, what if we were to throw the pizza box down instead of dropping it? This would change the initial velocity, but would it have any effect on the terminal velocity? Here we have a graph of the velocity over time of our drag model, but with an initial velocity of negative 1 meters per second in the y direction rather than 0. As we can see, the slope still evens out above negative 2 meters per second. Because terminal velocity is determined by the drag force, and drag force is proportional to velocity, the starting velocity will have no effect on the terminal velocity. So what do we take away? The constant force of gravity causes falling objects to accelerate towards the ground. A drag force that increases in magnitude in relation to the square of an object's velocity will prevent that object from accelerating forever. And when drag force becomes equal to the force of gravity, the object stops accelerating and terminal velocity is reached. Thank you.